It is 12 noon here in Happy Valley. Welcome everybody to today's virtual speaker session. We have another great program lined up for you today. We're going to be talking with Dr. Violet Major. She teaches physics and astronomy at Penn State Wilkes-Barre and is the director of the campus's Friedman Observatory. Look forward to having her share the great work that she's doing here at Penn State. As always, we'd love to know who you are and where you're from. Go ahead and drop that information in the chat and let us know where you're zooming in from today. Thanks for joining the Penn State Alumni Association Virtual Speaker Series. I see the Zoom room is filling up. We have a great crowd today. Over 125 people signed up for today's session, and I see some familiar names. Vicky, once again down in Harrisburg, joining us, and Diane in Berks County, and Midge Kennedy in Atlanta, Georgia. Dan Troxel, 78, now in Mechanicsburg. Good to see you, Dan. I see Dick Smith, a regular here in Appalachian, New York, from the class of 65, Amy in King of Prussia, and George in Littleton, Colorado. George, we're featuring a Colorado native today. Violet Major, a professor of physics and astronomy, is a native of Colorado. So a little bit of home cooking for you today. We got Jean in Florham Park, New Jersey, and Louise in Longview, Washington. All over the country tuning in today for our virtual speaker series. I see John down in Chincoteague. Beautiful place down there. Bernice, as always, in Mazatlan, Mexico, tuning in. And Marcia in Marietta, Georgia. We'll be getting started here in just a minute. Thanks for joining us. Where else would you rather be than a Zoom full of Penn Staters? I'm Paul Clifford, CEO of the Penn State Alumni Association, and I'd like to welcome everybody to today's virtual speaker session, which is being recorded. Live closed captions are available for this event. You can access by clicking the closed caption button at the bottom of your Zoom video window, and then clicking Show Subtitle. You can also customize your caption view by clicking the stream text link posted in chat. We are also live streaming today's presentation, and this live stream has been made possible through the gracious support of a donor for the Fund for Access, Ideas, and Audacious Goals. Today's presentation will be archived and available on our website after the event. This afternoon, we welcome Dr. Violet Major, who teaches physics and astronomy at Penn State Wilkes-Barre and is the director of the campus's Friedman Observatory. The Friedman Observatory, located at Penn State Wilkes-Barre, has been a beacon for education for Penn State students and the general public since it was built, thanks to a generous donation from the Friedman family. Its 16-inch Meade LX200 telescope is the largest in the region. This and the relatively dark skies of the back mountains make the observatory a great resource for amateur stargazers and professional researchers like Dr. Major. She will provide an overview of the observatory and highlights its role to the campus and to the community, including exciting cutting-edge research recently conducted there. Dr. Major received her Ph.D. in physics at Arizona State University with an emphasis in astrophysics. Her research topics include extragalactic studies such as the dependence of the galaxy structure on observed wavelength as it's related to galaxy formation and evolution, and improving the accuracy of distance measurements to galaxies to determine a more precise measurement of the cosmological parameters of the universe. Thank you once again for joining us, and I'm going to turn it over to Dr. Major now. Thanks for joining us, Violet.
Thank you. It's a great introduction. Thank you very much. So I'm very happy to be here to talk to you about Friedman Observatory. So it's located at the Wilkes-Barre campus, which isn't actually specifically in Wilkes-Barre. It's in Dallas, which is a few minutes away in the back mountains. So we've got this very beautiful location with in the forest, in the mountains. And so the skies are relatively dark compared to if we were inside of the city. And as you can see behind me here, we've got this gorgeous campus. The observatory is back here next to the Bell Technology Center. And then we got this nice big picture here of it during the spring. Very beautiful location. So I want to give you an overview of different things that are done at the observatory. If you would like further information about it, I invite you to visit these links that I have at the bottom, which should also be posted in chat. The top link is the official website on the Penn State website for Friedman Observatory. And then the bottom link is our Facebook page. The Facebook page is managed by the indispensable John Bellinger, who assists with a lot of different aspects of the telescope, including maintaining the equipment and hosting open houses when we have them. So the observatory used to have weekly open houses for the general public to attend. That was suspended due to COVID, but we would like to start that up soon. So if you're interested in visiting the observatory, I encourage you to keep an eye on these sites. Probably it'll appear on Facebook first. That's the best place to get up-to-date information. John Bellinger is really good at updating that. And it's even fun to visit that Facebook page, even when we're not doing anything, because he posts a lot of interesting astronomy news and so forth on there. He's managing that very well. Okay, so the reason we have this observatory here is because of the Friedman family. This picture here is of Sidney and Pauline Friedman, who donated the money necessary to build this observatory here. It had originally a smaller telescope inside the dome, and a larger one was installed in 2003, and these images are showing them doing that installation. It was purchased as an anniversary gift for Sidney and Pauline by their son, Rob Friedman and Anne Friedman Glauber. And that is what we currently have inside the dome. That's a Meade 16-inch LX200 telescope. The 16-inch means that that's the diameter of the mirror. It's 16 inches across. And the larger the mirror and the telescope, the more powerful it is, the fainter objects it can see. So the bigger, the better in the case of telescopes. And there's lots of different things that we use the observatory for. I'll go through them briefly. One of them is community outreach. This is a picture of one of the elementary classes from the local Lake Lehman Elementary School. They came to visit, and we have visitors like that from different groups, Cub Scouts and so forth, either during the day or the night, whatever is most convenient. At night, you could look through the telescope with the stars. During the day, you can't do that. But they could still get a tour of the observatory and walk up the spiral staircase to the top and look at that 16-inch telescope. We also have a couple of smaller telescopes that are portable that we can take outside and put on the lawn outside here for people to view through there as well. And also, we've recently purchased a solar telescope, which is portable, that we can take out to look at the sun. So that's what these students did. They got a tour of the observatory and looked through the solar telescope. So in addition to all these groups that we host, we also had the weekly open houses when weather permitting, which, as I said, is suspended due to COVID now, but those should be hopefully starting up again soon. So in addition to these sorts of things, there are also special events that we hold based on interesting things that are happening in astronomy. And so, for example, eclipses. So here's a couple of examples of some big events that we held. In 2015, the flyer on the right is advertising this super blood moon, which was an eclipse of the moon. So this would be called a lunar eclipse, and that is where the Earth passes in between the sun and the moon, blocking the light of the sun to the moon. So the shadow of the Earth basically is covering the moon. And you can see the progression here of what the moon would look like as the Earth's shadow is passing over it. It's always a full moon when it happens. And then the Earth's shadow begins to cover it and moves across it until, if it's a total eclipse, it completely covers the moon. And at that point, we get this really lovely red color that pops out. And that wasn't supposed to happen. Okay, really lovely red color that pops out because now only the red light of the sun can get through at that point, and the blue light is scattered away, so you can't see it. So it makes the moon this lovely blood red color. This is called a blood moon. And in this case, it was special because it was also a super moon. The moon orbits around the Earth in an elliptical orbit where sometimes it's closer to the Earth and sometimes it's further away in its orbit. And this just happened to coincide with it being closest to the Earth during the eclipse. So the moon looked bigger than usual. So it was a larger moon and also a total eclipse. So that was pretty special. And so we had this whole event surrounding it with refreshments and contests and things. And lots of people showed up to look through the telescope of the moon and to view it from our lawn in the sky. And later, also in 2017, a couple years later, we had a different type of eclipse. And this is a solar eclipse. So the difference here is that it's an eclipse of the sun. And it's where the moon passes in front of the sun from the vantage point of the Earth. And now the moon is casting a shadow on the Earth. And if you happen to be inside of that shadow, then you get to see the eclipse. And not everybody will be in the shadow because the shadow's smaller with respect to the shadow of the Earth. But we were lucky enough to be in that shadow. We were not lucky enough to be in the central part of the shadow where you get to see a total eclipse, but it was a pretty good partial eclipse. So we didn't get to see it completely cover the sun. But we made a really big event out of it. We had lots of things going on, crafts and contests and free food. And we handed out free solar eclipse safety glasses so that people could view the sun through the glasses safely. You shouldn't look at an eclipse just with your naked eye. And I've got some pictures of that event here. So we purchased 500 eclipse glasses, thinking that would be way more than enough, and we'd end up having extras. We're this small campus in the middle of nowhere in the back mountains, and we ended up having around 1,000 people show up, which really surprised us. So we didn't have enough glasses for everyone, but people could share, and we had other ways for them to view the eclipse. We showed them how to make pinhole cameras. So this image of the woman and her daughter are holding some of those where you make a pinhole and then let the light from the sun go through. Ordinarily, you would just see a round bit of light on the ground through that pinhole camera. But during an eclipse, you can see the little chunk taken out of the sun by the moon. And so it's like a crescent shaped shadow there. So that's one way to safely view it. And then another way is through the solar telescope, which we have. So this image on the bottom here is of one of the local elementary school kids looking through the solar telescope. This gold is a cute little thing. And then this is actually an advertisement in a local newspaper for the eclipse event that was about to happen. And then the image on the right is the eclipse event with that solar telescope. Instead of having the eyepiece so that you can look through it with your eyes, we set it up to a camera. And then that camera broadcast onto a television nearby so that people could watch the eclipse live happen on the television screen. And we had a really big turnout and everybody seemed to have a lot of fun, and it was a really great experience, and we look forward to doing more of these things in the future. Okay, so in addition to community and public events, we also use the telescope to support the campus and students on campus. Students can receive education with a telescope. I use it in some of the astronomy classes, and also can do research. So I just arrived here in fall of 2015. I have only been here for a few years. And before I got here, the telescope wasn't being used for very much other than the open houses. And I wanted to get research going on the telescope again. So that's an ongoing process where I'm trying to start up the research projects with the telescope. And we are just beginning doing that. So thanks to a donation from the Friedmans, got this new CCD camera to install on the telescope. So usually we would have an eyepiece here, and then you'd be able to look through using your eye to see whatever the telescope's pointed at. But we can also detach that and then attach the camera and then take pictures of the things that we're looking at in the sky. And then we've got, this is research quality, research grade CCD camera with filters that are also research grade. B is like a blue color, V is a green color, and R is a red color. And then you use these three filters to pick out light only in that specific color range. So you can learn how the light from each of those different filters is seen through that for each of the objects. So how does the blue light compare to the red light for your object? So when you take images with BV and R filters, it just lets in all the light and doesn't take a color image. So it's a black and white image, but then you can get 3 black and white images in BVR. Those are the 3 color channel, which you can then combine using a computer into a color image. And that's what the students did. So a couple of summers ago, I had 3 students that we started out our first student research program, and they observed 3 different objects, 1 for each of them. And then the students actually came to the observatory, made the observations, and then I taught them how to reduce the data. And they combined the 3 filters together into these lovely color images. So here's 2 of the 3 objects that the students took, and they made these images. This is, the top one is M82, called the cigar galaxy because of its shape. So this is a galaxy. The Milky Way galaxy is a galaxy that we live in. It's a collection of stars, gas and dust that is all gravitationally bound. And then outside of that, there are other galaxies. And this galaxy is 12 million light years away. So it'd take 12 million years for the light to get to us, or for anything traveling at the speed of light. So this is a starburst galaxy. If you look at the bluish color here, those are brand new stars that are being born at that time. And there tends to be a lot of really big, bright blue stars that are born in clusters during a starburst, and then they have short lives and then die away. And then you see more of the older, redder light from the redder stars. And this other object down here at the bottom is the Eskimo Nebula, named as such because it looks like maybe a human face in the middle, wearing a hood to protect the person from the cold. And this is a different type of object. So this is a planetary nebula, and this is inside of our own galaxy, so it's closer. Doesn't actually have anything to do with planets, despite the title. This is the result of a dying or a dead star. So as the star starts to die, there are very strong winds that blow the outer parts of the star away into this ring of gas around it. And then at the center then is what's left over, the small core of the star, and that's called a white dwarf. And it's glowing brightly in the ultraviolet, which is lighting up the gas surrounding it, which is the old outer layers of the star that were blown away. And then that glows for a while, maybe 1,000 years or so before it fades away. And each of these planetary nebulas are different based on how that gas was blown away. They have different shapes and really beautiful array of colors. And then the last one is the Orion Nebula. So this is in the constellation Orion. It was a lot bigger. So this is a stellar nursery. It's, again, within our own galaxy, so relatively close. It's a collection of stars that are being formed now inside of this nebula, which is a cloud of gas and dust. So brand new stars forming there. And if you're interested in further information about this project with the students, the link at the bottom is an article written about that. And that should also appear in the chat box. Okay, and finally, in addition to research with students, I'd like to get the observatory used more for professional research. And this was our big opportunity to get that started up. We were approached by scientists at the Southwest Research Institute in collaboration with NASA to help them to observe asteroid occultations. So an asteroid, big chunk of rock in space, and occultation is when it passes in front of something. So there are stars in the background and asteroids are floating by, and when they pass in front of a star, we can watch how it affects the light of the star behind it to learn something about the asteroid. The asteroids are very faint, so they're hard to observe directly, but you can see them as they pass in front of brighter objects behind them. So this is all in support of NASA's upcoming Lucy Discovery mission. This is a space telescope that they're going to be launching in October of this year, and it's going to actually travel 2 asteroids to learn more about them. And this emblem that they're showing here for Lucy, this is a cartoon of the satellite, and these 2 big round things are solar panels, and then it's visiting an asteroid in that picture. If you're interested in Lucy, there is a link to NASA's mission page right below that at the bottom of the page. Okay, so this picture off to the right is actually Friedman Observatory. This is inside the dome of our observatory. And this lady here is Roxanne Kamen. She is a member of the International Occultation Timing Association, was sent here by this collaboration to help us view the asteroid occultation. So she had to bring in a special detector that is specifically designed to view occultations. We wouldn't have been able to use our detector for this, and that's her setting up, getting ready to observe the event. So some more about that. Specifically, this type of asteroid that we're viewing is a Trojan asteroid, and its name is Orus. So the Orus asteroid, Trojan asteroid, what does that mean? If you look at this kind of a top-down view of the solar system, we've got the inner planets here, and then most of the asteroids are inside of the asteroid belt, which is this ring of asteroids between Mars and Jupiter. That's just a place where they're safe from Jupiter's gravity. If they get too close to Jupiter, Jupiter will fling them out into the inner or outer solar system. And then there's another couple places where they're safe from Jupiter's gravity, and that's at these what's called stable Lagrange points at 60 degrees ahead and behind of Jupiter's orbit. So they actually orbit around the sun in the same orbit as Jupiter does, ahead and behind it, and those are the Trojan asteroids, and that's where the Lucy mission is going to head. So in 2019, on September 7th, this our target asteroid, Orus, was occulting a star, and they observed this from Oman, not from here. So this is just an example of what it looks like for that to happen. So if you look at this picture, we've got a star in the middle, this faint star here, right in the center. I'm going to start a video and you'll be able to see what happens with time. Eventually, the asteroid's going to pass in front of the star, and you'll see the light blocked out by the asteroid. And there it is. For a split second, it disappeared. So you can't see the asteroid itself, but we can see that it was there from how it affected the light of the star behind it. And then we can gather all sorts of information about the asteroid shape and its orbit from that. So that's the sort of thing we wanted to capture here. And here we are with a map of the United States. So for the event that we were invited to help out was that was in October of last year of 2020. It's the same asteroid that you saw before, Orus, occulting a different star. So the star is very faint, but still the light from the star hits the Earth, even though it's very faint. And when the asteroid passes in front of the star, it casts a shadow on the Earth, a shadow from that starlight. And this is the path that the shadow took across the Earth. So it started in the northeast and then it moved down towards the southwest. And it just happened, you can see it's not a very big shadow, but it just so happened we were lucky enough that it passed right above Penn State Wilkes-Barre. So that's why they asked us to observe it. And they also had other observatories and portable telescopes across the path of the shadow to try to observe it. They need more than one data point to get the best information, the more the better, from lots of different vantage points to get the most information they can from the asteroid. So also on this image, you can see this white stuff, that's clouds. This was the prediction of what the clouds would be at the time that the event was supposed to occur. And it doesn't look good. Here in Pennsylvania, it was supposed to be cloudy. And then the shadow passed right at the edges of the cloud. And the only place that really looked like it would be clear was Texas, which isn't so good. But they had people waiting and watching anyway. And we tried anyway, and we set up. When I went out, it was cloudy. And we started setting up anyway, and then miraculously, the clouds started to disappear. And by the time the occultation happened, it was completely crystal clear outside. And then as I was driving home after putting everything away and driving home, the clouds came back in again. So it's like the skies opened up just for this moment. So we were extremely lucky, and we did get something. And here's what we got. So actually for 6 minutes, we took multiple 2-second exposures over and over and over again over a time period of 6 minutes. And that's just barely enough in the middle to capture the event. So there's 3 minutes before the event, 3 minutes after, and then right in the middle, we got a couple seconds of the asteroid passing over real quick across the star. And the star that we were observing is, I don't know if you can see it or not, but in the center here, there's these yellow lines that are pointing at the star, and there's this little barely visible fuzzy thing there. That's the star is so faint, it was right at the edge of the capabilities of the telescope of our size. They needed at least our size, if not bigger telescope to observe it. So, but we did get something, and they were able to extract some data out of that. And then we were one of the very few places that were clear enough to be able to see it. And then also they got some data from Texas. So they're still working on that results to be published eventually, but it's not ready for the public yet. So if you are interested in this story, there is an article also written about that, and the link is at the bottom there if you want to read more about this project. So that's all that I wanted to talk about in the highlights, and then we can open it up to questions. So about the telescope, just in general, used for community outreach and research and also education. So it's got a lot of different uses. I'll go ahead and stop sharing.
Excellent.
Yeah.
Excellent. Thank you so much, Violet.
You're welcome.
First question coming in is, what do you think is the most interesting discovery that you've made at the observatory?
So the only research project that we've had going on at the observatory so far within the last few years is what I just described with the Oris asteroid. So that's by far the most exciting. And we're still going on to find out what's happening with that. We didn't discover the asteroid, but we're measuring data that will help to learn more about that asteroid and to further help the Lucy mission, which is going to be traveling to the Oris asteroid in the future, I think to 2028 or so. And then before that, like I said, the research is just starting to get up again. There wasn't much happening before I got here with research. I think in the distant past, there was more going on, but it's been a while, so.
Excellent. You talked about partnerships with other observatories and other groups around the country. Are there other observatories within the Penn State system that you collaborate with?
We haven't collaborated with any others. If they'd like to, then I would like to as well. Yeah, let us know. Excellent. If there's anything that we can do.
And where are they located, for those who might not know? Where are some other telescopes located in the Penn State system?
As far as I know, there is one other observatory that's similar to ours, and that is it's in the Behrend Penn State campus, Mahalso Observatory. And then I think the University Park also has some telescopes on the roof of Davy Lab and a planetarium there as well. And I believe all of them are closed to the public now, like we are because of the COVID situation.
Right, but hopefully soon that will begin to open up. Other than being close to the public, how has COVID-19 impacted the work that you're doing? Have you done virtual programs to continue to deliver the kind of education you were previous to COVID?
We don't really have it set up to do that right now. So no, yeah. We haven't been able to use it as much lately, which is sad. And I've also been suspending student research with it until that gets sorted out. So we're looking forward to starting that up again as well.
Excellent. Someone is asking about the type of telescope that you use. I think we mentioned it's the Meade Schmidt Cassegrain LX200 telescope. Are there any limitations on that telescope that impacts the focus of your research?
There's various limitations. One is the biggest limitation for a telescope is its size. I mean, 16 inches, like you said, one of the largest in the area. But it's still not among the biggest of the telescopes, and that limits what we can observe. So the bigger it is, the fainter objects you can see. So there's a limit to how faint we can go.
Right.
And in addition to that, even though we're in a relatively dark area in the mountains, there's still light pollution here, and that makes it even more difficult to observe fainter objects. So a combination of that. If we're using just your eye looking through an eyepiece, there's a limit to how much you can see with that. The fainter night sky objects are going to be harder to see with the naked eye because of that. But if we use the detector, we can stare at a single object for a lot longer and collect light for a longer period of time. So you can see fainter things with a detector than you could with your eye.
Great. And I guess this is a related question, but they want to know, what's the farthest celestial body that you can see from your telescope?
So it depends on the type of object. So stars, we can see quite a bit of them, but the fainter object, like the objects where the light is more spread out, are going to be the more interesting ones to look at, right? Like nebula and galaxies and things like that. I'm not sure of the exact distance limit. It depends on how bright the object is. We would talk more about magnitude limits. But some of the deep sky objects are kind of a bit difficult to see with the naked eye looking through the eyepiece. But like that cigar galaxy that I showed,
right?
That's millions of light years away. You could just barely make it out with the naked eye through the eyepiece, but we got this much more beautiful, well-defined picture using the detector. So I'd say, yeah, you can see galaxies millions of light years away.
So a question coming in here, so much of deep space observation comes from radio telescopes. What do you hope the upcoming launch of the James Webb Telescope will do to further science, and what do you hope it can show us?
So the James Webb Space Telescope is unique in that it's viewing in a longer infrared wavelength than any other space telescope that we have out there, at least of that size. So it's going to be the largest, most powerful telescope in that wavelength range. And we're really excited about that because it'll be able to allow us to see things that we can't really see with any other telescope right now. So especially for me, that helps, that it's kind of goes hand in hand with the research I'm doing about galaxy evolution and formation, because it'll be powerful enough to be able to see the most distant galaxies in the universe, and to maybe even be able to resolve star clusters of the very first stars that formed. So I think I need to give some background on this. So as you're looking at further and further and further and further things, you're actually looking back in time. So we're able to look back into the past. And the reason for this is because light travels at a finite speed. So it takes a certain amount of time for light to get to us. So for instance, it takes about 8 minutes for light to get to us from the sun. So you're seeing the way the sun used to look 8 minutes ago, not the way it looks now. And if you're looking at a galaxy 10 million light years away, you're seeing how it looked 10 million years ago, not right now. And if you're looking at galaxies that are billions of light years away, like the most distant galaxies, you're looking at the way they were billions of years ago. And so as we look at more and more distant galaxies, which are getting fainter and fainter and harder to see, we're looking back into the past, we're into time. And then if we've never been able to see the very first stars before, but they think that James Webb Space Telescope might be able to do that. So that's really exciting.
That is exciting. Go ahead.
That's the most exciting for me, but then there's also a lot of other really cool stuff that it can do, because it's looking in a wavelength regime that can peer through dust, which usually blocks light. And so you can watch star systems as they form, planets as they formed, and see faint objects that glow in the infrared, like exoplanets and brown dwarfs and things like that. So a lot of things that we could discover that we can't see right now.
Excellent. Question from Daniel. He wants to know, considering the photographs you used from students, he wants to know what filters were used. It'd be interesting to see photographs of the same galaxy taken with different filters to compare. Can you describe how the photos would be similar or different?
So those are optical filters, Johnson, B, and R. So I would have liked to have gotten more filters, but we didn't have enough budget for it. You can also get filters that can view in the ultraviolet and the infrared, and that would definitely change the way they look. So that would be something that would be interesting to do if we could just get a different set of filters for that. So in the B filter, the bluer filter is picking out things that are blue. So that you see a lot of brand new star formation with that. So in the starburst galaxy, you could see a lot of blue. Same with the Orion Nebula. In the case of the Orion Nebula image that you saw, that ended up only having 2 filters combined. because there was a problem where we ended up not getting the third filter during the observing run. So we kind of cheated a little bit and just combined 2 filters together. It would have been even better if we had 3. And then another thing is that when you look at those images, they're not true color. Because we have these black and white images, and then when you put them through the software, you can change the contrast of each one and the brightness to whatever you want it to be. And then we just try to tweak them until we see something that looks good. So it depends not only on the filters you use, but also on how you combine those images together to get the color image in the end.
So Marcia would like to know if you're involved at all with the PSU SETI work.
I'm not specifically involved in that. That sounds like something that'd be really fun to be involved with, though. Yeah.
We had a presentation by those folks on one of these virtual speaker series, and it was fascinating. The search for extraterrestrial life is obviously what they're involved in, and fascinating stuff. It's but yeah, a lot of interest was generated by that presentation.
That's cool. Yeah, I'd love to check that out. Yeah, SETI is awesome.
Question here is there. So Amy wants to know, once you are able to open up again, is there a designated night to observe or to use the telescope to observe?
I think in the past we've had it on Friday nights, but that could change. It depends on the schedule of the person doing it and what's decided is the most popular date. Yeah, it'll probably be around the weekends. It's hard to get people to do in the middle of the week, right?
Yeah, absolutely. Question from one of our attendees here today, probably sparked by the answer to a question you just gave minutes ago. But is there any way to speculate on what happened to the objects you've observed that are millions of light years away? So if you're looking back in time, is there anything that we can learn by being able to look that far out or that far back?
So if you just look at a galaxy, at just a single galaxy, you're just getting a snapshot in time. That's what it looks like now, and you can't see how it's changed or anything, except for trying to maybe look at different stellar populations and saying, okay, well, based on what kind of stars we see over here, we know that this must have happened in the past with the birth of stars and so forth. If you want to get like an idea of just overall in general, what's been happening in the universe to galaxies in general, then you can compare a lot of galaxies at different distances and say, okay, galaxies closer to us look like this, and galaxies further away look different. So now we can kind of get an idea of what's happened during that time period to just statistically to everything. And so what we're seeing is that galaxies that are closer, they're more structured. We see more spiral galaxies and elliptical galaxies, and then galaxies that are very distant look more irregular and peculiar and kind of weird shape and look like train wrecks of just gas and stars just like everywhere. And so from that, we're building a picture of, in the past, they were smaller galaxies or proto-galaxies that then collided with one another and to form larger and larger galaxies. And over time, they settled down into the sorts of shapes that we're seeing now.
So a couple questions coming in here. Again, when we look at a galaxy that's billions of light years away, can we tell if that galaxy actually still exists today?
We would assume that it does.
Right.
Yeah, there could be galaxies that we saw in the past that have changed the most common thing would be they've collided with something else and merged with something else. And so it's not really that galaxy anymore. It's now something larger that's combined with other things. At this point in history, there shouldn't be galaxies that just disappear unless they're very, very, very low mass, and we're only able to form a few stars before they ran out of gas and can't form stars anymore. That's a possibility, but you would still have the lower mass stars should still be alive today. There hasn't been enough time in the universe for them to die off completely.
And how about new galaxy formation or very large black holes? Marcia's interested in your thoughts on the formation of new galaxies.
So formation of new galaxies in the context of black holes, or what's the specific question about that?
The question is, what are your thoughts on galaxy formation and very large black holes?
So very large black holes, like supermassive black holes. We're finding more and more as we look at galaxies that we're finding more of them that have supermassive black holes at their centers. And those seem to form pretty early on. And that'll just be, you've got the very concentrated area region in the center where gravity is centered at, and then you get enough stuff combining there that you form a black hole out of it once you get enough mass packed into a small enough space. And we're seeing more and more of those quasars and other active galactic nuclei, AGN, are supermassive black holes at the center of extremely distant galaxies, like towards the edge of the universe. So we see evidence of this, and those are massive black holes that are currently forming inside of those galaxies at the time, billions of years ago, that we're viewing them at. And so they're emitting very, very bright light that even outshines the galaxy itself, as a lot of material just keeps on falling into it. So, and this affects the formation of the galaxy too. It changes the shape of the galaxy because you've got a lot of matter falling in, and then you've got a lot of radiation coming out of it, jets of radiation and so forth. And that does have an impact on the evolution of the galaxy and how it will end up looking at the end.
So Michael wants to know, I'm sorry, Bernie is asking a question about traffic around Earth. He wants to know, will the number of satellites being sent into orbit around Earth affect your research?
So not really, at least not yet. It's not like it's blocking the light out. I mean, they're tiny enough. It's not gonna do very much to block out objects. And it's pretty rare to have a satellite go over an object that you're observing. Now, the longer the exposure time, the more likely you are to see this. And I have been observing at professional telescopes where I've been taking an image, and then when the image finally comes out, after you've been sitting on it for several minutes, there's a streak across it. And a lot of times that's a satellite. And then you just, if it goes across your object that you're interested in, you have to throw out that image and take another one. So it does affect it, but they're moving quickly enough. They're only temporarily there. And yeah, the more satellites they put up, the more often that's going to happen. But yeah, you just got to take more images.
Absolutely. So Violet, we want to thank you for joining us here on the virtual speaker series. Thank you so much for the presentation. And we'd like to thank all of you for joining us. As a reminder, we'll be hosting additional speaker sessions in the coming weeks and months. And this program's in addition to the wide array of online networking events and career programs that are available throughout the year. You can find the full listing at alumni.psu.edu/events. Thank you once again, and we are
Penn State.